Chapter 12 is where we're going. Notice the title. We're talking about surface area and volume. Now, surface area and volume involves what kind of figures?
Three-dimensional.
Three-dimensional. So all of this that you're going to see are kind of three-dimensional, okay? So just something to kind of keep in mind. Now, we're going to eventually, not today, talk about all the different types of solids that we can find surface area and volume. There's going to be a lot of formulas we're going to be learning. We won't do that today, kind of an introduction today.
There's one formula today, and I'll tell you guys that if it was me, I might start making a formula list for this chapter, because that's going to be a great thing to study with, and you will need to memorize all the formulas that we learn throughout this chapter for the test. So please be learning this.
Yes. And stressing that. Yes. Okay. Here's the deal. First section is all just talking about, exploring these solids. Solid is a three-dimensional shape, okay? So most of what we deal with in our world is three-dimensional, okay? So what are some things we're going to need to understand? Well, first of all, we have solids that we call a polyhedron, all right? A polyhedron is a solid, so it's three-dimensional, and it's bounded by polygons. So basically, it's something that you see a bunch of polygons making up that region. Okay. So polygons have sides, things like that. Now, the polygons are what we call faces. So we don't want to call the polygons sides. They're the faces of that solid. And it encloses a single region of space. Again, three-dimensional. Okay? Now, again, a solid, right, your solid, in a sense, is going to be, like, example of it would be like a Kleenex box. Okay. I'm looking at one in the room. Kleenex box would be considered kind of a polyhedron, all right? It has polygon faces, right? Now, we have, in a polyhedron, we have faces, which are the polygons. We also have edges. Now, edges is a line segment that is formed by intersecting the two faces. So kind of imagine you have your two polygons that intersect. They form a line segment. That's considered your edge, all right? So notice how we started. Polygons are the faces. The line segments are your edges. All right. In a polyhedron, we also have vertices or vertex, and those are points. We've talked about vertices before. These are where your three or more edges meet. Okay. So kind of breaking it down, polyhedron, all the polygon faces. Where the polygons meet are edges, which are line segments. Where the line segment or edges meet are points, which are considered the vertices. Okay, so just some basic examples now, or basic vocab. Now let's apply this vocab to this next slide. So I want you guys to try to determine how many faces, how many edges, how many vertices are in this polyhedron. And again, this is a polyhedron because these are polygons, okay, that faces. Okay. So go ahead and do it and check with us. So pause it, come back. Okay, so if we were answering this question, first of all, guys, I want you to notice that when you draw a three-dimensional shape on a two-dimensional surface, it can be kind of challenging. So one thing to notice is that there's these dotted kind of segments. That kind of shows that it kind of has that dimension. There's polygons kind of behind the polygons that are in the front. Right. All right. So it doesn't always look exactly how it should if you saw it in front of you physically. Okay. So just keep that in mind. It kind of is a distorted look. Okay. So if I counted how many faces, now faces are what?
Those are the polygons themselves.
Okay, so if I counted how many faces I had, how many did I get?
Well, I have 4 around the sides, and I had 1 on top, 1 on bottom, so we've got a total of 6.
So again, how we did that kind of, this is a face, all right? This is a face down below.
So there's our top and bottom.
And then you have your side, so this is or this kind of on the side of it. Okay, this is a face, and this is a face behind, a face here, and then a face in front. Okay, you don't have to color them in, but if it helps kind of do that, then feel free to do that.
Sure.
That one won't go back for some reason.
That's okay.
I don't know. All right, let's go to edges.
All right, so edges are where two faces meet.
Okay.
So I'm looking at along the top part, I see 4 edges right there.
So these are all edges because, again, they're the segments.
Right. And then I see along the sides where all those side faces connect, 4 more there.
Okay, but notice if you do this where the sides connect, you already counted this one, right?
Oh, I'm just talking about around all the sides because I've already counted all the tops. Sorry.
Okay.
So there's coming down from the top
So you're talking about 4 down here and 4 up top.
Okay, sure. I was talking about the side ones. That's okay. Let's do that. So 4 at the top, 4 at the bottom. So far that's 8. Then along, like going from the top to the bottom, I have those edges on there as well. So far I'm at 8, but then I'm going to go from the top to the bottom of that segment, and then that, yeah, the ones in the back. There we go. So then there's 4 more there too. So there's a total of 12.
Okay. Now, the next one is vertices. How many vertices? Now, vertices, where do we find the vertices?
The vertices are where those, really it's going to be 3 segments that are joining together at a point. So it's all the points. It's all the corners. And I see that there's 4 at the top, and then there's 4 at the bottom. So a total of 8 vertices.
And that's all you have to do. So you're just counting, kind of looking at what you're doing. I'm going to have us come back to this question once we learn the new theorem. Okay?
All right. Okay. So we have 2 vocabulary terms that we wanted to address with talking about polyhedron. And we've seen this word regular before. Regular is a polyhedron whose faces, so all the polygons, are all congruent, regular polygons.
So if they're congruent, that means they're all going to have the same shape and size. So you're going to see all like the same type of polygon.
Right.
And regular, meaning that each polygon is going to have congruent sides and angles. So like a regular polygon that comes in mind is like a square. So you're going to see all of the squares that make up this polyhedron all the same or congruent squares.
So congruent square faces on every part.
You could have regular pentagons. You could have regular hexagons, but all of them are going to be congruent to each other.
Exactly. Convex. We've talked about convex and concave before. So convex is a polyhedron such that any 2 points on its surface can be connected with a line segment that lies entirely, so connected by a line segment, that lies entirely inside or on the polyhedron. And I know that the convex definition is always a little tricky for some people, and it says if the line goes outside the polyhedron, it would be considered concave. Most of us are comfortable with looking at a figure and determining if it's convex or concave, because we know that if it's concave, it's caving in. And you'll notice this one kind of caves into that polygon up top. What this is saying is if I draw a line segment that connected these 2 points, notice that line segment is entirely outside of that figure. Where if I connect any 2 points here, it's either going to be on, or if I go through the middle of my polygon, that's not very straight, but you can picture it.
It goes inside of it.
It goes inside. So it can either be inside or on to be convex. If you realize that you could connect a segment or make a segment connecting points and it's outside of the figure, that would be concave.
And guys, typically, thinking about the polyhedrons are made of polygons. So if you see one of its faces is a concave polygon, then that means it's going to be a concave polyhedron. So most of what we're going to deal with are going to be convex polyhedrons, okay? So most of them are going to be where they're not going to be caving in a sense.
Right.
All right. Now, another vocab, lots of vocab today, is this idea of a cross-section, okay? So what is a cross-section? It is the intersection of a plane and a solid. Now, a plane is 2-dimensional. A solid is 3-dimensional. So it's kind of like you're like slicing through a 3-dimensional shape. Right?
I would say, if you guys have ever played Fruit Slice before,
yes,
this is a perfect example of a cross-section. Because where you slice that fruit, you're going to notice that you are left with really a 2-dimensional surface at that intersection.
Like if you take, and you're talking about fruit, like I think of like an orange. If you cut an orange in half, what you're looking at on the 2-dimensional surface is a cross section. Okay,
Right.
So cross section is the intersection of plane and solid. So here's the deal. I have a bunch of solids drawn here, and we took a plane. Now plane is kind of looks like more like that parallelogram, but a plane is just 2-dimensional. So you're just slicing through it in a sense. So when you slice through this particular solid, when they say what cross-section, they're going to ask you to describe the shape of the cross-section. So do your best. I mean, you would need to know a little more about some of these solids, but if you look at it, kind of look at this cross-section, and we kind of made it a little bit darker here in red here. What would this plane be represented?
It's a pentagon.
It's a pentagon. So again, all the cross-sections are going to be two-dimensional. So you're going to be describing it as a two-dimensional shape. So what about this one?
Well, it looks like it's an oval or an ellipse at this point. Actually, it ends up being a circle.
Yeah, because think about, first of all, the solid. The solid here is actually a sphere. We're going to talk about those later. And if you slice along a sphere, you're going to end up with a circle every single time, like the orange example.
Right. Okay? And keep in mind that when you're looking at looking at this three-dimensional shape, as you cut it two-dimensionally, you're not going to see the depth of it. You're not going to see the dimension.
Kind of distorted, so it does distort it. Okay, what about this one?
That one is another pentagon.
And it's kind of tricky because it looks like almost like a trapezoid, but there's this little side right here. So another pentagon. All right. What about this bottom one?
Well, if it's a cube, that would definitely be a square. I don't know that it's a cube or not for sure. So I could say rectangle, and I'd be okay with that.
Yeah. Too. And really, if you said even like a parallelogram or a rhombus, it does kind of in a sense look like a cube, so probably square. We'd probably accept if you said rectangle as well. Just because, again, like remember what I said, we need to know a little bit more about that solid. And eventually, guys, we're going to be doing that. All right, what about this one?
That is a rectangle, actually. It looks kind of more like a parallelogram, but again, because it's on that angle, it's hard to tell.
And think of this as like a can of soup. If you slice along kind of on that can of soup, you're going to see a rectangle. Yeah. All right, last one.
Last one is a triangle.
Now, in this picture, you're going to notice that, and going back a little bit, kind of tying vocabulary together, are all of these considered polyhedrons?
No, they're not, because they're not all bounded by polygons.
Which ones would be?
The two in the middle, the middle top and the middle bottom, are not polygons, faces, so therefore they're not polyhedron. The rest of them would be.
So the rest, kind of the outer rim, are all polyhedrons.
Right.
Good.
Okay. Platonic solids, there are 5 regular polyhedron, and we talked about the regular polyhedron a little bit already. To be regular, it means that all of the faces are congruent regular polygons. So in this case, we're looking at just what are they, all right? And I'll tell you guys that this is not something we're going to make you memorize these names. We just want you to be aware of the fact that there are 5 regular polyhedra. They're named after the Greek mathematician and philosopher Plato. We've talked about Plato probably before. The tetrahedron would be when I've got regular triangles, equilateral triangles. And it takes 4 of those equilateral triangles to form a regular tetrahedron. A cube is formed by all square faces. So there's 6 squares that are all congruent. When we talk about a regular octahedron, we're talking again about those equilateral triangles, but it's almost like taking 2 regular tetrahedron and putting them on top of each other. A regular dodecahedron, if you look at that, notice that there are all regular pentagons, but there end up being 12 of those regular pentagons. That's where they get the dodecahedron from. Same thing, octahedron came from the 8 faces that form that. When we talk about an icosahedron, that's 20 faces and they're all equilateral triangles.
Looks like on like 3 of them, I noticed, are all dealing with equilateral triangles.
Yeah, and so that really is the most basic regular polygon, and there are more that you can make with that than anything else.
These are just named after Plato, so these are kind of popular in that way. Now, will you have to draw all of these and deal with all of these? No. I would say out of all of these, the ones you're going to see the most are these 2, the first 2.
Yeah, and I think we've maybe even got an octahedron
these
in there
2,
too,
and then this one probably also, you're going to see that. Very rarely, and I don't know if we ever really
I don't think we ever do. And honestly, guys, again, you're not going to need to memorize the names. Other than cube, you should know what a cube is, but the rest of them would be okay.
Okay, now this next one is a theorem. Now, how would you pronounce that name, Mrs. Hochgraby?
Well, everybody wants to say Euler, but it's Euler.
It's kind of weird, isn't it? Euler's theorem, which is also named after another famous mathematician out there. This theorem involves this idea of your faces and vertices and edges involving a polyhedron. Okay, now this is one, if you know Ms. Hooker mentioned about the formula list, this is one formula that you want to add to your list. Okay, so you might have a separate list going and have this added to it. Okay, now Euler's theorem is basically saying you can take the number of faces plus the number of vertices, and that's going to always equal the number of edges plus 2 for any polyhedron. Again, this only works for polyhedrons. So if it doesn't have polygon faces, this wouldn't make sense because you wouldn't have polygons, you wouldn't have vertices, you wouldn't have edges. Okay.
Right.
Now, I'm going to go back to the slide. Where was that? Where was this one?
It was, I think, 2.
Yeah. Okay, so Euler's theorem said faces plus vertices equals edges plus 2. And I know that in your classwork, there's going to be a problem that's going to say, do this, what we did here, and then verify it. So if I asked you to verify this formula, or theorem I should say, you're basically going to check to make sure, okay, does the number of faces plus the number of vertices, really does that equal the number of edges plus 2? And you just simplify. So this is 14, this is 14, we're good to go. So this is kind of checking your work. So that's kind of cool. So when you start counting, you can always verify with that theorem because it works every single time. Okay?
Awesome. Now, the other thing we're going to do with that theorem is we're not going to give you the solid itself. We're going to give you some information about the solid, and you get to find the remaining information about the solid. So if I tell you a solid has 11 faces, 5 of them being quadrilaterals, 6 of them being pentagons, the question will be how many vertices does it have? Now, oh, we skipped one. I'll tell you what, let's go ahead and go back to this one first, and then we'll get to that next one. Okay, so this one says a solid has 10 faces. Sorry, guys. 10 faces. 4 of them are going to be triangles. 1's a square, 4 are hexagons, and 1 is an octagon. So we have all kinds of different faces here. The question again, how many vertices does the solid have? So let's think about that formula again. It was faces plus vertices equals edges plus 2. Do we know any of these pieces yet?
Well, they tell you 10 faces, so we know the F, so we can put 10 in.
Love it. 10 plus the vertices we know we don't know equals, and we need to know the number, somehow the number of edges.
Okay.
Because we need to only have one unknown.
Yeah, because it says how many vertices does a solid have. That's going to be our only unknown. So, and right now we actually have 2 unknowns. So we have to find the number of edges first.
Okay. Now, let's go back to the example that we had before. When you look at comparing the faces, which we do know, and the edges, do you see any relationship that might exist? And even just comparing the faces compared to the edge.
Well, the faces times 2 gets you the number of edges.
Do you think that's going to happen every single time?
Well, well, each face has, there's 6 faces, and each of these faces in this case have 4 sides in a sense. Right. I'm going to kind of think of it about this way. So really, all 6 of those faces, if I have them all have 4 sides, that would make 24 sides, right?
Right.
But, and that's not the same thing as edges, because every side actually shares a side with another polygon. Okay, that's their intersection.
So you notice, like, for example, this polygon has 4 sides. And the one up top had 4 sides, but together these 2 sides together make an edge.
And every polygon has to make an edge together. So the 24 total sides divided that in half, because we're going to basically do that. That's going to get the number of edges. So in this case, that's why that works.
That might be something good to write down. If I take the total number of sides of all polygons and divide by 2, that should equal our edges. That's a good relationship to know, because there's a lot of times where you're not going to be given the number of edges. But notice they went in depth with us and said, find the right one now. They said that of those 10 faces, 4 were triangles.
Okay.
So what do you know about total number of just sides of a triangle that we're going to have there? How could I figure out the number of sides within all those triangles?
Each triangle has 3 sides, so 4 times 3. That's going to be 12 sides.
Okay.
These are sides.
Keep track of sides, yeah.
1 square is going to have 4.
Yeah, I could say times 1.
Mm-hmm. Okay. And then 4 hexagons. Each hexagon has 6 sides, so that's going to be 24. And then 1 octagon is going to have just 8 sides. So I'm going to add all those together, and that's going to get you 48.
So that's 48 sides that are all made up. However, again, it takes 2 sides to make 1 edge.
So I'm going to divide that in half. So the total edges is 24. Now, I remember you asking that question earlier. You're like, do you see a relationship between the faces and edges? And I said it was doubled. Notice this one, 10 times 2 doesn't get us 24. So, so you said, is that going to happen always? No. So we got to keep in mind. So that work off to the side that Ms. Hochgraby did, that's what you're going to have to do each time.
And notice, and the reason that it worked on the last one is because they were all the same type of shape. They're the same number of sides.
Exactly. This one had triangles, squares, hexagons, octagons.
Exactly. So just be careful with that. But now, we're not done yet because we haven't found vertices. So what are we going to do to find the vertices here?
I would just, I'm going to add the 24 and the 2 together, and then I'll subtract 10 from that 26. So that's going to get vertices is 16 vertices.
So Euler's theorem allows us to be able to find an unknown number of vertices or edges or faces knowing the other pieces.
Okay, guys, this next one, this is how we started talking about it. Now, this is one I'm going to encourage you guys to actually try on your own and then check with us. So pause it, come back. All right, so we're dealing with a polyhedron. We are dealing with faces, and they're saying find the vertices. Now, we know the number of faces plus the number of vertices is always equal to edges plus 2. Now, what is it we already know?
We know faces.
So we know that. So I can go ahead and put in 10 plus vertices. This is going to be
11.
11. The last one was 10. Sorry.
That's all right.
11 plus vertices. This is our unknown. That's our question mark. Equals. Now, do we know the number of edges?
Not yet, but we can find it.
Okay, so that's the one we're going to try to find, plus 2. So let's go and find out these edges.
Okay, so for the faces we have 5 quadrilaterals, so 5 that have 4 sides apiece.
So that's going to give you 20
sides.
Okay, I'm going to stress that. We're finding the edges, but we're finding the sides first. And then we also have...
We have 6 pentagons, which are each 5 sides, so that's going to give us 30.
And so that's
30
again, sides. Now, if I add those together, I have a total of
50 sides.
50 sides. But I know each side in one polygon with another share. So we're going to do what with that?
Divide by 2.
So the edges is
25.
25. So we're going to put that back in here.
Okay, so our 11 plus V is going to equal a 27. And if I subtract an 11, I'm left with 16.
Now, does that mean we're always going to get 16 vertices? No, just happened the 2 that we did had that case. Okay, so something for you to keep in mind.